Okay. Near the end of the last class, we talked about representations of Lie algebras, and we talked about a particular representation, the regular representation. Let me just remind you that a representation of a group is basically a homomorphism from the group G to either GLV, where V is some vector space, the set of all general linear transformations on the vector space, or to a subgroup of GLV. The reason why we have to specify subgroup of GLV is because to us, when we define homomorphism, we said homomorphism from G1 to G2 will be both a map which preserves the structure and also be onto. Now, some authors don't use the onto restriction. They just say homomorphism from G1 to G2 is a map which takes elements of G1 to elements of G2 in such a way that phi of G1, G2 is phi G1 times phi G2. Now, if we were to use that definition of the homomorphism, we could just as well drop the subgroup part of this statement. Okay? You could just say it's a homomorphism from G to GLV if you're talking about representation of group G. So basically, what happens under a representation is the abstract elements which could make up a group gets a more concrete version, basically linear transformations acting on a vector space. And of course, they become even more concrete if you choose a basis and replace the linear transformations themselves by the corresponding matrices. And so product of linear transformations, which of course product of group elements should translate to product of linear transformations, which is do one transformation after the other, and that in turn transforms to the product of matrices, the standard matrix multiplication rule. Now, for Lie groups, the same thing happens. Every Lie group element would have to map onto some element of the subgroup of GLV for this to be a representation. Of course, because the group elements themselves depend on parameters, the corresponding linear operators on GLV would also depend on the same bunch of parameters. And also, if you want to talk about matrix representations, we'll have a bunch of square matrices. Could be a finite bunch, could be infinite bunch. But there should be one matrix for each group element. So the matrix should depend on the parameters we specify the group element. This is for representation of groups, in particular Lie groups. Now, if you talk of algebras, essentially the same kind of thing happens. When you say it's a representation of a Lie algebra, it again is a homomorphism, not from G, but of course the Lie algebra is, let's say, L. It's a homomorphism from L to a subalgebra of basically the Lie algebra corresponding to the group GLV. Remember, the elements in GLV are linear operations which occur, which take vectors to other vectors. Basically, LinV is nothing but the tangent space to that. That becomes even easier to understand when you think in terms of matrices. GLV translates, when you talk of matrices, to basically GLN, right? N by N square matrices which are invertible. If you take these N by N square matrices which are invertible, and you look at the identities neighborhood, what you get are matrices which are close to the identity. And they form a linear vector space under addition. But what is more important is because matrix multiplication is an associative product, this associative algebra also gives rise. So first thing that you have to realize is GLV only has invertible matrices. LinV has all matrices basically, all square matrices of size n, where n is a dimension of the vector space V. I'm talking of the matrix representation of LinV here. And just like GLV, LinV also has matrix multiplication. The only difference could be that there could, of course, be matrices, in fact, there are matrices in LinV which cannot be inverted. Or there are linear transformations in LinV which cannot be inverted. I'm going to use matrix or linear transformation sort of interchangeably, since you all know the connection between the two. Of course, the connection is not unique. a given linear operator can stand for many, many different matrices depending on your choice of basis. But all that I'm pretty sure you're familiar with. So hopefully, if I say matrix in place of an operator, it's not going to confuse you too much. Now, one important thing that you have to realize is when you talk of matrices, you not only have a product structure, which essentially gave us GLV, you also have a linear vector space structure. You can add two matrices to get a matrix, you can multiply a matrix by a number to get a matrix. And this actually produces an n square dimensional real linear vector space. Right? A bunch of n by n matrices will give you an n square dimensional real vector space. So you have already had the first ingredient for LinV to become a Lie algebra. At least you have a linear vector space. Then you need a product. Now matrices already has products, the standard matrix product, and that product is associative. Because that product is associative, we can always form a commutator of that matrix product, that is AB minus BA, and that becomes a valid Lie bracket in LinV. So your original Lie algebra could be a very abstract Lie algebra with a very abstract bracket defined. You may not have any other notion of what that bracket is, except to know what the bracket of xy turns out to be. There may not be any further explanation as to where this particular bracket of xy came from. But you know that xy bracket has to obey the basic properties. Okay? So what we are saying here is instead of the abstract bracket, the representation gives us a way of a more concrete realization where the commutator of the matrices of the linear operators in LinV or their corresponding matrices essentially standing for the bracket, like for the abstract bracket. Now, one thing which is important is this homomorphism and this homomorphism, of course, mean two different things. Homomorphism is basically a map which is going to preserve the structure. In a group, the structure is basically a product. So when you say homomorphism, you always mean in a group, phi of G1, G2 is phi G1, phi G2. And when we are talking about representation, of course, phi G1, phi G2, and phi G1, G2 are all invertible square matrices. And this product here is simply matrix multiplication, whereas this product here between G1 and G2 is a product in the original group. Of course, that's old stuff. When we are talking of homomorphism from L to a subalgebra of LinV, basically what I'm talking about is a map which will take two elements, let's say small l1 and small l2. Oops. Okay, color changed. Anyway, I hope you can all see this. Yes?
Yes, sir. Yes, sir.
Okay. So if you take two elements, L1 and L2 from the Lie algebra, form their Lie bracket, and then carry out the map, you are going to get the corresponding Lie bracket in LinV or its subalgebra, phi L1, phi L2's bracket, but this bracket in this case. So that's the structure preserving thing. You have a map and it preserves the basic structure of your group. Of course, because the linear Lie algebra is not just a algebra. Okay, it is an algebra with a Lie bracket, but it of course is a linear vector space to begin with. You must also have a linear, this map should also be linear, that is, it should obey this structure.
I'm sorry, sir. It can be linear or it should be linear?
Which one?
No,
So this one has to be linear. Sorry.
has to be linear.
I said can, then I made a mistake. This map that we are talking about has to preserve the basic structure in a Lie algebra, which means it has to, for any homomorphism, it has to be a linear map. It has to be bracket preserving. Do the bracket after or before, doesn't matter. And in the specific case, when you're talking of a representation, where you're representing group elements or mapping group elements to linear operations on V, then this bracket actually is the commutator. That is AB minus B. So the abstract bracket gets replaced by a more concrete bracket, the commutator. Okay? So any questions so far? And the particular representation that we talked about, we will see representations over and over again. After all, whenever we apply Lie algebras, especially to quantum mechanics, we're essentially looking at the action of Lie algebra elements on some vector space or the other, space of states. So you would invariably end up with some kind of a representation of an abstract Lie algebra. But the one Lie algebra representation, which is the most important one for us as far as the theory is concerned, is the so-called regular representation. And this, of course, as we say, is a map from L. And to a linear space of operators on L itself. Remember, L is a vector space in its own right. So linear operators which act on L can very well furnish a representation of L. Of course, to talk about a representation of a Lie algebra, we'll first have to start with some vector space V, and then talk of all possible linear transformations on that vector space V to itself. Here, the V happens to be L itself. And the particular map that we talking about here has a specific name. You call it the adjoint map, or just write it as AD. And what does it do? It acts on a particular group element, so algebra element. X is an element of this algebra L and maps it to a linear operator add X. This is a linear operator which is a member of this lin L, which means it's a linear operator which acts on the elements of L. In other words, a linear operator from L to L. And what does add X do to a element of L? If you take the element Y, it gives you X comma Y. So that's how you define the regular representation. You map every element of the Lie algebra to a corresponding linear operator which acts on the Lie algebra. And it acts on the Lie algebra via the Lie bracket. Okay? Yeah. And here the Lie bracket, because we're talking of linear operators acting on the space, here the Lie bracket actually could also be represented pretty easily by commutator brackets. In other, not this bracket is the original Lie bracket. I may have spoken too soon. This is the original Lie bracket of your Lie algebra. But because add X and say add Y are linear operators acting on L, you can of course define the commutator bracket of add X and Y. And we work it out the other day. This is going to be add of X comma Y. Which is simply the same thing as saying you apply the map, let's call that phi again, let's call add phi and say add X is phi of X. This is phi of X, comma phi of Y's commutator bracket is equal to phi of the bracket X comma Y, which is exactly what you need for a representation. And how did we derive this? We derived this using the Jacobi identity. This is a direct consequence of the Jacobi identity. Okay. Everything clear so far?
Yes, sir.
Okay. Now, we will make plenty of use of this adjoint operation, or later on we will see many cases where we will be using the adjoint operation maybe without saying so. Because we will be essentially using things like eigenvectors of the bracket operation, which we remember we talked about that last day. Things like J3 comma J plus is J plus. This doesn't really look like an eigenvalue equation when you look at this. It's really saying that the bracket commutator of J3 and J plus is equal to J plus. But if you look at this from the point of view of the adjoint operation, this is some linear operator at J3 acting on the vector, the element of your vector space J plus, which gives you J plus itself. Okay. So sometimes when you think about this, it becomes a bit more complicated, especially for physics students to sort of follow this because in physics, especially in quantum mechanics, we already have a vector space, which is the Hilbert space of states on which describes the states of the system. And then on top of that, you have operators acting on them. But what we often don't realize or don't keep in mind is that the set of operators themselves form a vector space, right? So these are the operators acting on your Hilbert space in quantum mechanics. Add J3 is an operator which acts on this set of operators. So it's an operator if the set of original operators the set of original operators form a vector space. Operators like add J3, etc., act on that vector space, not the original vector space. Okay, and so sometimes we sort of take the liberty of calling them some things like super operators, operators which act on operators as operators themselves. However, basically the whole idea is operators which act on vectors themselves form a vector space, and you can have operators acting on those, which of course belong to an entirely different set. Now, when you write it like this looks obviously like an eigenvalue equation, right? And it is an eigenvalue equation. So all these ladder operators, etc., that we have been using basically are eigenvectors of the adjoint operator in some sense of that. Okay, so it's obvious that we will be using this over and over again. Now, since add x here is an operator, it will also have its matrix representation the moment you choose a basis on your Lie algebra. Of course, this basis would have to be the basis of the Lie algebra itself, or the underlying vector space of the Lie algebra. And if you do that, how do you translate an operator to a matrix? You make it apply. You apply it on some basis vector, let's say Ej. You get another vector, of course, and you write that as a linear combination. So basically, the matrix corresponding to X is Kjth element, right? Is that okay? So add X will have a corresponding matrix, which of course will depend on X. And that matrix, the elements of the matrix will be defined by the same way as every linear transformations matrix is defined. Okay? Yeah. Here note K is the first index, second J is so if you think of this in terms of row by column matrices, K is the row index, J is the column index. And that using the row index, this Kj instead of Jk thing in this sum is exactly what we did. We did in linear algebra to ensure that multiplication of the operators, which is doing one operator after another, corresponds to matrix multiplication. Okay? So I can get a matrix for every one of the add x's. But since x's are members of this linear vector space, the Lie algebra, it's obvious that if I just know the corresponding adjoints for E1, E2, E3 up to ER, I would immediately know what adjoints for any linear combination of E1, E2, E3, ER can be. So basically, this is something which we need to look at, add of EI. The ith basis vector, the corresponding add to that, if you know this for all the i's, that is I running from 1 to R, you automatically know add x for every x. Right? Okay. Yes?
Sir, sorry, can you repeat, like, how is this the basis for that thing?
No. First of all, E1, E2 up to ER, this is a basis.
Yes.
Of the Lie algebra.
Yes, right? But like if you're saying if we know add EIs, When you're saying we know all the
any
values.
x in EI will be CI, right?
Yes, yes.
Okay, I can
Okay,
use
okay. That's fine.
Okay, then I think you should be able to figure out that
Yeah.
add x is actually CI times add EI. Just use the definition. You take add x as commutative with any arbitrary y, you'll see that this works out. Okay? If you know the add EIs, you know everything. So basically, in a Lie algebra, what we do is choose a basis. Of course, we can always do that because there's an underlying vector space. Corresponding to the basis vectors, we just focus on the adjoint operators corresponding to the basis vectors. And in the matrix version, we just look at the corresponding matrices for add EIs. So you will have one such matrix for every I, that is R such matrices. And they together will essentially tell you all you really want to know about the regular representation. So whatever information you want about the regular representation is already there in those matrices. Now, when you look at the specific form of those matrices, according to this general rule, how you actually write down matrices corresponding to operators, this should be, okay, this adjoint corresponding to EI will have a matrix. That matrix we will call TI. So you have T1, T2 to TR. But TI is kjth element times EK, right? This is simply the rule for linear operators to matrix transformation. But now, by definition, what this is EI is commutative with EJ. And what do we know it to be in terms of structure constants? Right? Remember, once you have a Lie algebra and you have an abstract Lie bracket, if you can tell me what is the Lie bracket between the basis vectors, you have told me all possible Lie brackets. Right? That follows from the fact that Lie brackets are ultimately linear. These are bilinear, linear in both the factors. And so these are the only commutators that only Lie brackets that you should really worry about. And these numbers are exactly what we call the structure constants. Now, can you realize what the matrix elements of T1, T2, T3 are, etc.? These matrices are going to be. So Ti, from here, you can see that this and this has to be the same. And since the E's are all basis vectors, so they're linearly independent, you must have Ti's, Kj's. The kjth element of the matrix for Ti must be Ck, Ij. So basically, what you could do is, some books actually do this. They don't give you all the background about regular representation, the adjoint operation, all that. I think Georgia is guilty of. Okay, Georgia may have improved on that in a later edition. In the original edition, he definitely did that. He just said, okay, let's take a bunch of matrices T1, T2, T3 up to TR. How do I define the matrices? The kth row jth element of these matrices are just the structure constant Ckij. So the ith such matrix is Ckij. And then he went on to show that these matrices actually form. Okay, these matrices actually have the same commutation relation that you would expect from the structure constants, from the original, that is the same commutation relation as the original Lie bracket. But he didn't call it the original Lie bracket, he just called it the original commutator. Because he was dealing specifically with particle physics applications, where the initial Lie algebra that you deal with is definitely a Lie algebra of some kind of operators, with the Lie bracket essentially being a commutator. I think in the later edition, he did define what a regular representation is a bit more carefully, and then came on to this. But this is fine. If you are given a bunch of matrices, T1, T2, T3 up to TR, whose row column values are given by these, you should be able to check just to make sure. Let's do the check just to make sure. Although from the way in which we arrived at this, it should be obvious that we should really get Ti, Tj's commutator bracket to be Ckij, Why are we sure of this? Because we are sure of this because this, after all, we already know that the regular representation is a representation, right? By the way, how did we know that? We knew that because of this result. which is a consequence of the Jacobi identity. So Jacobi identity told us that this representation x mapped to add x is actually a representation of the Lie algebra, and therefore any matrix version of that we have already that's sort of obvious. In a matrix, what happens is the linear algebra product, that is composition, gets replaced by matrix product, and the linear algebra commutator bracket gets replaced, of course, by Lie algebra commutator bracket, right? Or sorry, matrix commutator bracket. Okay. Now, just in case somebody gave you these matrices T1, T2, T3 in terms of the structure constant, and did not give you how they arrived, how they were arrived at, of course, you would then have to still check that this is true. You do realize that the approach that we have taken guarantees that TITJ's commutator should be CKIJTK, right? But let's say we didn't realize that. Let's say we want to check. How would I check? I would essentially check that the matrix you form, this of course is a matrix, TITJ minus TJTI, the ABth element of that, which of course is TITJ's ABth element. So we'll just calculate that. Straight, no tricks or no other, nothing else. You just calculate this ABth matrix element. And what is the ABth matrix element of the product TITJ? Yes. Tell me.
PIKJ.
No, first of all, TIs. Just thinking of the TI's element, TI and TJ's individual elements. It's going to AK, TJKB. Is that okay? This is this one. Mine is the same thing with TJ, AK, TI, KB. Is that okay? This is just matrix product, nothing else. I'm just rewriting the formula for how you multiply matrices. And then replace this TIAK with CAIK. This is CKJB minus CAJK CKIB. What would the next step be? Can anybody suggest that? Let me just point out one thing. K. The K is a dummy index here, right? So downstairs, we have three indices I, J, B. Here you have I, J, B. Here you have J, I, D. That should give you a good enough hint as to what to do next. What should your next step be? Whenever you have pairs of products of, you have two products of pairs of C's.
Jacobi identity.
Yeah, but to use the Jacobi identity, what you need is IJB. Remember, okay, Jacobi identity would mean cyclically permuting the three lower indices which are free, not the dummy ones. So not K. IJB, K will stay where it was. That's fine. That's already there. And the upper index A also stays where it was. You don't tamper with them. But to get to use the Jacobi identity, what you should do
You have to change the last term to
the last term.
CKBI.
Well, it will be a plus anyway, but that's easy. CKBI. That gives you IJB, JBI, two terms in a cyclic permutation. So obviously, this is given by C minus C. Okay. The third permutation. Third permutation will be E IJ, right? Okay. And then use the fact that this is C. There's a minus sign, make it a plus. So what is this? This is Ckij times Tk's ABth element, right? This one is Tk's ABth element. This is just the structure constant. So at the end of the calculation, we have managed to convince ourselves that Tij is Ckij Tk. Here, of course, this is, although this is a Lie bracket, this is a specific Lie bracket, the commutative bracket between the matrices Ti and T. And even if I had not arrived at this by starting from the regular representation and finding matrix elements, we just said that, okay, let's take the structure constants themselves and use them to form matrices. Of course, the structure constants have 3 indices. A matrix should have 2. So one of the indices, so if you're forming one matrix, you form R different matrices. I here stands for which matrix you're talking about, and K and J for the row and column matrices. The moment you do that, you end up with a bunch of matrices whose commutative bracket exactly mimics the Lie bracket structure of the original Lie algebra. That is, has exactly the same structure constant. Okay? These matrices are going to play a big role in the rest of the theorem.